Hello viewers, welcome to Add-on. In this question, we are asked to explain the band theory of solids. Okay, so let us start with it. So band theory of solids, it is just a theoretical model which explains the state of the electrons in the solid materials. Right. So electrons, right? This electrons lie within valence band or conduction band. And what is this valence band and what is this conduction band? I am going to explain it now. So one thing before explaining that, we need to know that electrons, they can either lie in the valence band or they can lie in the conduction band in the solids. And depending upon this configuration of electrons, solids, they can be classified into three types. Okay. Any type of solid in the universe can be classified into three types. Either it will be a conductor, or it can be a insulator, or it can be a semiconductor. Okay. Depending on this band theory of solids, the electronic configuration within a solid gives us three models of solid, which are conductor, insulator, and semiconductor. So at first, we are going to discuss about the valence band, conduction band, and there is another band present which is called forbidden band. But the thing is, electron doesn't lie within this forbidden band. So these are the three energy bands, right? We call them as energy bands. These three bands basically dictates the configuration of electrons within a solid. So at first we are going to discuss about the valence band, then we are going to discuss about conduction band, and then we are going to discuss about forbidden band. And before this discussion, we just need to have a clear idea that the electron will either lie in the valence band or in the conduction band. It will not lie in the forbidden band. Okay. So what is a valence? What is a valence band? So valence band is particularly an energy band, okay, that consists of the valence electron energy levels, right? As it contains the valence electron energy levels, it is known as a valence band. For example, for any kind of, I am considering any kind of atom. Suppose the configuration is 1s1, 2s2, 2p3, like this, okay? So these are all valence band. These are the particular bands in which the electrons are present. For example, in first, we all know this principle, this conduction principle, right? That the electron will at first lie in the 1s cell, then it will move to the 2s, then it will move to the 2p. For example, if the number of electrons here I am considering 7, then 2 electron will reside in the 1s cell, then it will reside in the 2s cell, and then remaining 3 electron will reside in the 2p cell. And the energy level of this particular cell, for example, if I draw the energy diagram, this is the energy level of the 1s cell, which is at the ground level. Okay, this is the 1s cell. Then next higher energy level is the 2s cell. Next higher energy is the 2p cell. Then we will be getting 3s. Then we will get 3p, like this. Okay. So the thing is, valence band is the particular band in which the valence electron resides. Okay, this is the valence band. So here the valence electrons are only residing. But in the conduction band, here in the conduction band is the energy band that consists of free electrons. And now for the electrons to be free, external energy must be applied such that the valence band electron push to the conduction band and become free. For example, if I draw here, this is a particular valence band. Okay, this is a valence band and this is the conduction band. Okay, so in the valence band, as I have said earlier, the electron configuration is 1s2, 2s2, 2p3. So there are a total of 7 number of valence electrons which are present in this valence band. Now initially conduction band is free. Okay, no electrons is present in the conduction band. So as I have said, conduction band is the energy band in which free electrons resides. So in order to electrons to become free, for example, this electrons is 2 plus 2 plus 3, these 7 electrons. If we want to make these 7 electrons free, we need to move these electrons from the valence band up to the conduction band. Okay. And as soon as these electrons enter into the conduction band, they become free. Okay. So, for example, there is an electron. For example, the two electrons from the 2p cell changes from valence band to conduction band. So now those two electrons become free. So they are now lying in the conduction band. Okay, so this is about the conduction band. And what is the forbidden band? As we can see, there is a gap between the valence band and the conduction band. It is not like that we want to excite an electron from a valence band to the conduction band, and by applying a minimum amount of energy we can do this excitation. This is not true. We have to give a certain amount of energy to overcome this energy gap. Okay, this is an energy gap. This is also known as energy gap. This is also known as band gap, or this is also known as forbidden energy gap. Okay, so we need to apply that particular amount of energy to the electron in the valence band to overcome this energy gap and go into the conduction band. So the energy gap or the energy level which is present between the valence band and the conduction band, this is known as forbidden band. Okay, so based on this configuration of conduction band, valence band and the forbidden band, we are getting three configuration of solids: conductor, insulator and semiconductor. Okay, so let us explain it one by one. So at first, in conductor, so what happens in a conductor? In the conductor, the next higher energy level or the conduction band is present in very close proximity to the valence band. Okay, so as a result, with applying a little amount of energy, we can easily excite the electrons from the valence band to the conduction band. Suppose this is the conduction band here. Okay, I am denoting it by CB, which is the conduction band. And here we can say that the top of the conduction band and the bottom of the valence band, the top of the valence band and the bottom of the conduction band are coinciding with each other. They are this portion, they are coinciding with each other. Okay. So as the energy bands are coinciding with each other, we can say here the forbidden gap, or I am saying I am representing the forbidden gap or the energy gap, or the we could say band gap between this conduction band and the valence band by del of Eg. This is almost equals to 0. Okay. So electrons, they can easily transit from valence band to the conduction band. And as this electron transits from one state to the higher energy level, there is a flow of current. Okay, there is a flow of current. So this movement of electrons facilitates the flow of current. So that is the reason this type of solids are known as conductor. Okay, and what happens in insulator? Insulator, there is also a conduction band. This is the conduction band, and there is also a let me denote it here. There is also a valence. Okay, this is the valence band. There is a valence band, and this is the conduction band. Okay. And here we can see that the two bands, they just overlap with each other. But here we can see the distance between the conduction band and valence band is typically very large. So we can say this is the forbidden energy gap or the band gap. I am assuming del of Eg here is almost 14 kilojoule. Okay. So in order to excite an electron from the valence band up to the conduction band, we need to apply more than 14 kilojoule of energy. Okay, so that energy will result in the movement of electron from the valence band to the conduction band, right? So here the energy gap, it is very much high. So for this reason, the flow of current will be very much less, or we can say negligible. So as it doesn't prefer the flow of current from the valence band to the conduction band, or there is no flow movement of electrons from the valence band to the conduction band, there is no flow of current in the insulator. And for this particular reason, these solids are belonging to the category of insulator, which means they are not a good conductor of heat or electricity. On the other hand, this conductor, they are a good conductor of electricity. Now the next group of solid will be semiconductor. So what happens in a semiconductor? This is the conduction band and this is the valence band. Okay. So here the energy gap is neither too high, neither too low. So it is neither 0 or it is not 14 kilojoule. It doesn't have a value which is as low as 0, or it doesn't have a value which is as high as 14 kilojoule. So for example, here the energy gap is almost 5 kilojoule. So what happens during this scenario? That depending upon the external condition, it will sometimes act as a conductor and it will sometimes act as an insulator. Suppose I am assuming at T is equal to 10 degrees centigrade, the energy gap this get reduced up to 2 kilojoule. Okay. So during that time, the energy gap will decrease and we will easily we can easily excite the electrons from the valence band to the conduction band by application of energy. But for example, if T is equal to 30 degrees centigrade, and during that time, energy gap will increase up to 20 kilojoule. So during that time, the band gap increases. So for that reason, electrons cannot be excited from valence band to the conduction. So during this time, there is a movement of electrons. So during this time, it will act as a conductor. But during this time, the band gap is high. So the movement of electrons will be less, or we can say there is no movement of electrons. So as there is no movement of electrons, there will be no flow of current. So during this time, it will act as a insulator. So that is the main reason that is this type of solid or this group of solids are known as semiconductor, because they are not perfectly conducting, or they are neither they are perfectly insulating. So that's why they belong to the group of semi. So according to the band theory of solids, these are the three groups of solid that exist in the real time world. Thank you.